Hello, Integrated Math 1. Welcome to Module 2, Topic 1, Lesson 1. So we've already done the warm-up. We've already done our getting started activity. We've already been playing around with our arithmetic sequences quite a bit, and we're going to play around with them a little bit more today to see what happens when we start graphing them and looking at tables and cool things that start to happen here. So I have for you, just to start off with, I've got 4 explicit formulas up above. Each of these explicit formulas, of course, represents a different arithmetic sequence. And again, you know how this works. You know the basic formula. I'll write it down. I want my pen. There's my pen. You know the basic formula and how this works. You know that it's a sub n equals a sub 1, which is your first term, plus your common difference, sometimes called a constant difference, but a common difference d, and then your n minus 1. And you know this formula, you've seen it before, you cherish it, you love it, all that good stuff. So you can see I have 4 different explicit formulas here. So your first term, your common difference, your first term, your common difference, first term, common difference, first term, common difference. You get the idea. You can see what's happening here. So here's what I've done. On page M2-9, you have, along with these 4 explicit formulas, you have 4 graphs A, B, C, and D. Now, taking what you know about the explicit arithmetic formula, you know what the first term is, you know what the common difference is, if it's going up or down, that sort of a thing, increasing or decreasing. I would like you to take that information and I would like you to match the explicit formulas with its graph. So again, some strategies you might want to use would be, okay, well, what's the first term of my arithmetic sequence and my explicit formula? And what's the common difference? Positive, negative, is it increasing, decreasing? That's going to give you a lot of information to help you match your formulas with your graphs. So go ahead, hit pause to match everybody up, and then hit play when you're ready to check your work. All right, let's match this up. We're going to match this up. You ready to match this up? So here's the deal. I'm going to start with this first formula right here. I can see that I start with 2. My first term should be 2. That's a -4. That's a 2. Okay, good sign, good sign. That's a 2. All right, good sign. So B and C are good. Ooh, that one starts all the way up at 4. So it looks like I've narrowed it down to B or C. I can see that my common difference is a -4. That's a -4. So that means I start at 2, but I go down, right? I'm decreasing. So that means if I have to choose between B or C, since they both start at 2, well then shoot, I'm going to choose B because it's going down, it's decreasing. Let's see, for this lovely guy, it looks like I start at -4. So my first term is a -4, and then it goes up 2. So, graph A starts at a -4. Do any of the others? No, they do not. So I'm going to go with graph A for that guy. This lovely formula right here, it starts at 2 and then it goes up 4. So no, that starts at 2, but it goes down. That starts at 2 and goes up 4. It does. Up, up, up. Sweet. So I'm going to pick graph C for that guy. And for this last one, I'm in process of elimination, but still we'll make sure we're doing this right. So for this last guy, I start at 4, and then it looks like I go up by 2s. So -4, 2, 2. Oh, here we go. This one starts at 4, and sure enough, it keeps going up 2, up 2, up 2, up 2. So graph D it shall be. Wonderful. That wasn't so bad, right? I mean, you know what the first term is, you know if it's going up or down, so that kind of made it not too bad to match up your graphs. Very doable. Now, looking at all 4 of those graphs that you just made, I would like you to consider the set of graphs that we were just playing with, and I'd like you to identify the function family represented. Linear, exponential, quadratic, piecewise, absolute value. What is it? So I'd like you to identify the function family that it belongs to, going all the way back to our first unit, and based on these formulas and graphs that we were just playing with, do you think that all arithmetic sequences belong to that function family? And explain your conjecture. And don't freak out over the word conjecture. A conjecture is a mathematical statement that appears to be true but has not been formally proven. So go ahead, hit pause, give me the function family. Do you think all arithmetic sequences fit into that function family, and why? So hit pause, jot down your thoughts, and then hit play, and we'll continue the discussion. All right, so first of all, I hope you noticed these graphs all belong to the linear function family. They all made straight lines. They were dots, but if I were to connect the dots, they all would have made straight lines. So this definitely feels like these graphs belong to the linear function family. So I'm going to say that the graph of any arithmetic sequence is linear, because both arithmetic sequences and linear functions have what we call a constant rate of change. Yeah, we call it the common difference, but remember that the common difference is when we're adding or subtracting by a constant. Yeah, it's constantly add 4 or subtract 3 or whatever it is. So yeah, I'm going to go with that. I'm going to say, yeah, they are going to fall in that category. Thank you, constant rate of change. We'll get more with constant rate of change in a bit here. So let's take a closer look at the relationship between the arithmetic sequences and the family of linear functions. So you know a lot about each of these relationships, right? We've been playing a lot with arithmetic sequences. And last year you played a bit with linear functions, although we're going to play with them a lot more today and this whole school year. So on page M2-10, you have some stuff here. So the explicit formula, right? Our explicit formula, hello. And the table of values that represents graph C, hello, are shown. So here's graph C from earlier. We've included our arithmetic formula, right? This guy right here, arithmetic sequence, and here's our explicit formula, a sub 1 plus d equals n minus 1. You know this, you know this. And we've included a table of values. So term numbers here, and of course, term number 1 we know is 2, but we also know we're adding 4. So 2, 6, 10, 14, on and on and on. And of course, those points are graphed over here on the graph. Yay. So I have my formula, my graph, and a table. We're going to do some stuff with these guys, and we're going to start seeing where these relationships all meet up. So to start off with, I would like for you to describe the domain of my sequence. And when we're talking about domain, remember we're usually talking about our inputs, our x values, what we're plugging in for n. What do you notice about these numbers that you're plugging in for n? That's going to be your domain. Hit pause to jot down your thoughts. Hit play when you're ready to check your work. So I don't know about you guys, but I noticed that my term numbers were always positive whole numbers, right? Like 1, 2, 3, 4. There's not going to be any fractions in my term numbers. There's no such thing as, there's a first term and a second term and a third term. There's no term 3.4. No, that doesn't happen. So there's not going to be any fractions here. There's not going to be any decimals there. It's just, this is the number of terms I have. You have a term or you don't have a term. So I'm going to describe my domain in this particular case with this sequence as all integers starting with 1. Sometimes you can call them natural numbers. If you say all positive integers, that would be okay as well. There's a lot of different ways to word that. And now what I would like you to do is, can you identify the common difference? Notice it says in each representation. I know you can find the common difference in the explicit formula, but see if you can find where that common difference is on your graph and where that common difference is in your table. I'm making you think now. So go ahead and hit pause, jot down some thoughts on that. You can draw on the graph, draw on the table, and then hit play when you're ready to continue the discussion. So again, the formula was easy. I know what my D is here. I know what my common difference is on my formula, right? We've done this. We did this so much last unit, didn't we? So I know that my common difference is this guy right here, sitting right there. Oh, so it looks like my common difference is 4. So D equals 4, yay. But the real trick is where is that on the graph and on the table? So looking at my graph, I can see that every time I move over 1, I go up 4. Over 1, up 4, over 1, up 4. Yeah, there's my common difference. That's right. My common difference is right here on my graph. I go up 4, up 4, up 4. So D equals 4 because I keep moving up 4 units every time. Believe it or not, your common difference D, that 4, is also on your table as well. But where is it? Well, it's actually pretty easy to find. If you were to subtract any 2 terms, because I keep going up by 1 on my x values here, then that means if I were to do 6 minus 2, I get 4. 10 minus 6 gives me 4. 14 minus 10 gives me 4. It's a common difference. That's right. If I subtract any 2 terms, I can get my any 2 consecutive terms, I should say. That totally gives me my common difference. So it looks like your common difference is in your table as well. It's everywhere. All right. Let's take this a little next level. So are you sick of looking at those dumb little dots on your graph? So fine. What I would like you to do now is to draw a line to model the linear relationships seen in the graph. That just means connect the dots, people. But don't just connect the dots. Remember that lines go forever and ever in both directions. So use that whole graph to draw your line. And here's the tricky bit that might take you back to last year, and you may have to remember a few things. It's been a while. I would like you then to write an equation to represent that line. See what you can do. So draw a line and give me an equation for the line. Hit pause to work that out. Hit play when you're ready to check your work. All right, so the first thing I did, I drew my line. Connect the dots. La, 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 la. Look at that line. It's so pretty. I did, of course, put arrows on either end because we know lines go forever and ever and ever in both directions. Ooh, and I also had to write an equation. So because it was linear, I was thinking back to my previous math class, and I thought, oh, yeah. Linear equations. They did the whole y equals mx plus b thing, right? Right? You remember that? And m was your slope, and b was your y-intercept. Well, I was looking at my graph and realized I kept going up 4 over 1, up 4 over 1, up 4 over 1. So my slope is 4 over 1, also known as 4. Remember that b is your y-intercept, so where does it hit your y-axis? Well, it's like put arrows on either end and made a nice big line. Looks like it'll hit my y-axis right at -2. So my slope is 4, and my b value, my y-intercept, is a -2. Yay! But this looks different than our explicit formula, right? I mean, because we said the explicit formula was also an equation that also represented this line. So something's up here. So let's see if we can start to bring this all together. Before we do that, actually, I would like you to describe the domain of my line, my pretty, pretty line. Oh, my pretty, pretty line disappeared. There it is. It's back. I missed it. It's all good. I would like you to describe the domain of our linear model. So we said for the sequence, the domain was all positive integers starting at 1, right? But what about when I put a whole line on it instead of just a sequence? What's your domain now? Hit pause to give it some thought, and then hit play when you're ready to check your work. So when we were looking at it as a sequence, we said there were no decimals, no fractions, nothing in between. But when I'm dealing with a line, I could totally have like 1.5 and find an answer, right? 4.3 and find an answer. So it now includes everybody, and it goes forever and ever in both directions. So I'm going to say that the domain of this graph of the linear equation model is all real numbers. When it was a sequence, I couldn't have like the in-between bits, but now I can with my full-on line. So my domain is now all real numbers. So we were just saying that our our sequence equation didn't quite match what we ended up with when we wrote our y-intercept equation, right? Our slope-intercept equation for our line. And why did they not look the same? So it turns out an explicit formula is one equation that you can use to model an arithmetic sequence, but you can rewrite the explicit formula for the arithmetic sequence in function notation. Yes, we can. So here we go. Don't forget that for a linear function, function notation, if you recall, looked like f of x equals ax plus b. We played with this a little bit way back in the first unit. And we just said that a and b were just numbers, some kind of numbers that we plugged in there, positive, negative, wholes, or fractions or decimals. We really didn't care. They all did the same thing. But so I want to get this bad boy here to be in this form. So let me show you how it's done. It's not that bad, but it does require some actual math. Watch out for that. So here's our equation. A of n equals 2 plus 4 times n minus 1. And this is the explicit formula that we're used to using from last unit. But I'm going to change it to function notation. So first thing I'm going to do is I'm going to take this a sub n, and I'm going to rewrite it as f of n. And it's a lot easier to write it that way. It's a lot easier to type it that way. Many of you guys already discovered that. So I can turn my a sub n into f of n. Now, I still need it to look like this, ax plus b, where a and b are just real numbers. And I certainly don't have that going on yet. And I like this form of ax plus b because a is my slope and b is my y-intercept. So I like them. I want to get it there. So what I'm going to do is I'm going to work with this back end. First things first, parentheses. You know that you can get rid of parentheses by using the distributive property. You can do for, ooh, sorry, my pen, it went weird. Fine, be that way. Hang on, it's coming back. Nobody panic. So I'm going to use distributive property. It's not that hard to do. It's pretty straightforward stuff. Let me bring my pen back. So I can just go, okay, well, 4 times n, if my pen will write correctly, maybe it will, maybe it won't. 4 times n, and then I can do 4 times negative 1. Sorry for the bad writing. It's not working out there. So I'm going to keep my 2 out the front, and then 4 times n is 4n, and 4 times a negative 1 gives me a negative 4. The next thing I notice here is that I have some like terms. I'm going to move some things around. So I want my variable to be the front guy. So I'm going to just switch these two right here. So I now have 4n plus 2, and I still have a minus 4 on the back. And of course, we can totally work out this guy in the back here. 2 minus 4, of course, gives us a negative 2. So a sub n equals 2 plus 4 times n minus 1. This lovely explicit formula, we can use some distributive property and flip some things around and combine our like terms to make it into function notation. It can be written in function notation as f of n equals 4n minus 2. And now I can see my a value is 4, and I can see my b value is a negative 2. So my slope is 4, and my y-intercept is a negative 2. Yay! So what I'd like you to do, can you just take a moment to compare the equation you wrote to model the graph? Hang on, what page was that? What number was that one? Nobody knows anymore. So sad, so sad. Hang on. I know what page I'm on sometimes, some days, most days, a few days. Make sure I'm on the right page. So what I'd like you to do for question 7 is I would like you to compare the equation you wrote on number 5. So the equation you wrote on number 5, right? I think on number 5 we wrote y equals 4x minus 2, right? That was the equation we wrote on number 5. I would like you to compare that equation with this function model that we just wrote. What do you notice? Go ahead and hit pause, jot down what you notice, and then hit play when you're ready to continue the discussion. I don't know about you, but I noticed they're almost exactly the same. There are some differences, right? There are some differences, but they have the same slope. They have the same y-intercept. Now, the only difference is that instead of a y, we have an f of n or an f of x sitting over here. So, I mean, it's a tiny bit different, but really, we're just using x's instead of n's, and we're using f's instead of y's. But it really is the same equation. It's not your imagination. It's the same stuff. So the next thing I would like you to do is compare your common difference with your slope. There's something really important we need to catch here. Look at the common difference from your arithmetic explicit formula and look at the slope of the equations we've just been writing and tell me what you notice. Hit pause, jot it down, hit play when you're ready to check your work. I don't know about y'all, but I noticed that the common difference of an arithmetic sequence is the slope of the linear function. Yes, it is. Yeah, that common difference gives you the slope of your function. Remember constant difference, constant rate of change? Oh, they're all related. They're all related. Oh my gosh. So Hank has some ideas here. Now that we're feeling good about the slope, we're feeling pretty good about the slope. But Hank is a little confused when it comes to the y-intercept. So Hank said that the y-intercept of a linear function is the same as the first term of the arithmetic sequence. Why is Hank wrong? Tell me why Hank is wrong. Go ahead and jot down your thoughts on why Hank is kind of incorrect on that, and then hit play when you're ready to keep talking. So the deal is that the first term of your function is when x equals 1, isn't it? Like when n equals 1, x equals 1, right? That's the first term of your function. But remember that a y-intercept is when x equals 0. So they're a little bit off, right? So Hank's reasoning is incorrect because all of our sequences begin with term 1. All of our sequences begin with term 1, which means they always begin with when x equals 0. When x equals 1, I can say this right. But the y-intercept of a linear function is when x equals 0. Yeah, so they're a little bit off, just a little bit off. We always start our sequences with x equals 1 with term number 1, but a y-intercept on a graph on a linear function is when x equals 0. So it's just a little off is the problem. Always feeling a little off around this place. All right, let's go to activity 1.2. Now that we have the feel for these things, for the slope being the common difference, for the fact that the y-intercept is always a little bit off from the first term of our sequences, let's play with that a little bit. So at the end of the last show, stagehands at the community theater stack the audience chairs and place them in storage. Fair enough. The height of one chair is 34 inches, and as each additional chair is stacked, the height increases by 8 inches. And if you've ever had to help stack chairs, you know exactly what I'm talking about. So what I would like you to do is I would like you to write an equation using the explicit formula, arithmetic sequence, explicit formula to represent this scenario. So go ahead and hit pause, write out your explicit formula, and then hit play when you're ready to check your work. All right, so explicit formula, a sub n equals a sub 1 plus d times n minus 1. A sub 1 is my first term. Well, I know the first chair is 34 inches. And then d is my common difference. And we said that as I keep adding chairs, it keeps increasing by 8. So that would be my common difference. So my first term is 34. My common difference is 8 as I add more chairs on. Yay! Now that you have this lovely explicit formula, and it is a lovely explicit formula, now that you have this explicit formula, I would like you to do a little work on it, and turn it and rewrite the explicit formula in function form. So if you need a little help doing that, remember you can go back to page M2-11 where we had that worked example in the box. If you need a little help trying to turn your explicit formula into function form. And then we'll define our variables, okay? So go ahead and hit pause, do your work, hit play when you're ready to check it. Keep going. All right. So I took my lovely explicit formula. First thing I did is I distributed that 8. So 8 times n, and then 8 times a negative 1. So 8 times, actually I take it back. First I changed my a sub n into f of x. That's what I did first. And then I did 8 times n, which is 8n. 8 times a negative 1, which is a negative 8. I switched these around a little bit. I just moved these guys around so that my 8n would be out in front. And then, of course, 34 minus 8 gives me a 26. Now, I should be careful here because I put an x there. And that means I really should have turned that n into an x as well. In fact, I'm gonna just write over it. It's going to be tacky, but you know what? Go with it. And I would be like, that's supposed to be an x. And I just turned it into 8x plus 26. And so here's the deal. I'm going to say that x represents the number of chairs that I have stacked up, and f of x represents the height of the stack of my chairs. So we just took our lovely explicit formula, turned it into function form. X is going to be our chairs, and f of x will be how tall our stack is. And now what I would like you to do is I would like you to compare these two algebraic representations of a scenario. Compare the explicit formula that you made on question number 1 and the function form that we just did on question number 2. I just want you to compare these two guys, right? I want you to compare your whole a sub n equals, and remember it's a sub 1 plus d times n minus 1. And that gave us this, right? Sorry, I like seeing it on the same page. For you, it's on the same page. I had to go to the next page. And then we said that function form looked like this, and it gave us, sorry, man, there's sometimes my pen is weird. Sorry, I'm gonna fix that. And so then we said that was ax plus b, and so in this case that meant that f of x equals 8x, and I think we ended up with plus 26. Yeah. So I would like you to compare these two representations. It's the same scenario, but I have two different equations now to represent them, two different algebraic representations. So I would like you to compare the value, and I'm going to get this over here. There we go. I would like you to compare the value of d in your explicit formula to the value of a in your function form. How are they represented? Don't forget to include your units of measure. Go ahead and hit pause, jot it down, hit play when you're ready to check your work. Of course, they're the same, right? Our common difference, the value for our common difference is 8, and the value for our a value is also 8. I'm just going to make sure I throw in those units of measure. So the value of d and a both represent what we'll call the unit rate. In this case, it would be 8 inches per chair that you add on to your stack. And using those same formulas, I would like you to examine the value of a sub 1 from the explicit formula, that first one, and relate it to the value of b in our function form, how are they represented in our scenario? Go ahead and hit pause, jot down your thoughts, and then hit play when you're ready to check your work. So I know that a sub 1, that 34 in my explicit formula, is the height of the first chair, all right? So I know that a sub 1 represents the first term of the sequence, or f of 1 of my function. And it represents the height of a stack with one chair. So if I only have one chair in my stack, is it really a stack? Who can say? But I know that that's what a sub 1 represents. However, when I'm looking at b in my function form, remember that b is when x equals 0. So I'd have 0 chairs? Not exactly. So in function form, the expression b represents the y-intercept, or f of 0 of the function. So it represents the height of a partial chair. Of one, sorry, that should say one, not on, of one partial chair, not counting the top 8 inches, which is weird. I guess you cut off a chunk of the chair. It's rough. Next up, again, looking at these two representations, our explicit formula and our function form. If a sub 1 represents the first term of the sequence, which we know it does because we're smart like that, what does a sub 0 represent? And can you rewrite that arithmetic explicit formula so that you use a sub 0 instead? Deep thoughts, deep thoughts. Hit pause, give that some deep thoughts, and then hit play when you're ready to keep going. So, okay, I was giving this some thought. So if a sub 1 is the first term, a sub 0 would be the height of one partial chair, just without counting that top 8 inches. Because a sub 0 would be our y-intercept, wouldn't it? Yeah, it would. So how could I rewrite my arithmetic sequence, right? Because we usually have a sub n equals a sub 1 plus d times n minus 1. But what if I don't want to use a sub 1? What if I want to use a sub 0 instead? There is a way to rewrite it. I'd write it like this. Yeah. Oh, sorry, I've got a sub n in here twice. My bad. That's awkward. But a sub n equals a sub 0 instead of a sub 1. And that means I need to change the back end. I'm still going to have plus d, but now instead of n minus 1, I just have n. Because I already subtracted 1 off of here, so now I don't have to subtract 1 back there. It's weird, but go with it. So in this stacked chair scenario, both d and a represent the additional 8 inches of height per one chair, or the unit rate of change, right? That's what they are, our slope, our common difference. It's really just a constant rate of change. It's just that's how much we're adding on each time. So the common difference d of the explicit formula is the same as the slope a of a general linear function. They both represent constant change. So in a sequence, the common or constant difference is the difference in term values between consecutive terms, right? We noticed that we could find our common difference just by subtracting two terms that are next to each other. In a linear function, the slope describes the direction and steepness of the line. And it is the difference in the output values divided by the difference in the corresponding input values. Are you looking at this over here? Are you looking at this over here? Does this look familiar? You may want to circle that bad boy or highlight it or something, because for our next lesson, it's going to be really useful to remember. So we know that in a sequence, we just subtract the two terms next to each other, and that gives us our constant difference or common difference. But we know it's the same as the slope on a linear function. So if you remember, you could find the slope of a linear function by subtracting your y values and then dividing that by finding the difference in your y values and dividing that by the difference in your x values. difference in your output divided by the difference in your input. This is kind of bringing it back a little ways. So when you see a graph or rewrite an explicit formula for an arithmetic sequence, it's pretty apparent that it represents a linear function, right? We graphed it and we're like, well, that's a linear function. And even when we were playing with the formulas, we could rearrange it to make it look like a linear function. We're like, yeah, it's a linear function. However, the structure of a table requires other strategies to determine whether it represents a linear function. So if I gave you a table and said, hey, is this table a linear function? How would you know? So one strategy is to examine what we call first differences. First differences are the values determined by subtracting consecutive output values when the input values have an interval of 1. So that sounded complicated, but let me explain. If your input values, your x values, are just counting by 1, 1, 1, 1, 1, 1, 1, 1, then you can just look at the difference between two consecutive output values, two consecutive y values. So if the first differences of a table of values are constant, then we say the relationship is linear. So if you keep subtracting and you're getting the same thing every time, it's linear. So if I keep subtracting two consecutive y values and I keep getting the same thing, guess what? It's linear. And we call this finding the first differences. I'm going to show you what I mean. So the tables that represent the explicit formula and the function form of the stacking chairs scenario are shown up here. So I've got my stacking chairs. This is my explicit formula. We start at 1, right? So 1 chair is 34, and then 2 chairs is 42, 3 is 50, 4 is 58. And then, of course, we have it in function form, only we started at 0s, 26, 1 is 34, 2 is 42, 3 is 50. And notice my x values are just going up by 1. So 1, 2, 3, 4. I just keep going up by 1. And same thing here. I just keep going up by 1. 0, 1, 2, 3. So this means that we can check first differences. And we said that first differences just means that for every single one of these, you're going to subtract these two, see what you get. Subtract these two, what do you get? Subtract these two, what do you get? And you're going to keep doing that here. Subtract these two, what do you get? Subtract these two, what do you get? Subtract these two, what do you get? So I'd like you to do that. I would like you to take a moment to determine the first differences in each table to verify they both represent a linear relationship. So go ahead and hit pause, do all your little subtractions, find all of your first differences, and then hit play when you're ready to check your work. All right, so I'm going to find my first differences. Are you ready? I got my pen at the ready. So I'm going to subtract these two to start with. If I do 42 minus 34, I get 8. And then I'm going to subtract these two. 50 minus 42 also gives me an 8. And then I'm going to subtract these two. 58 minus 50, of course, also gives me 8. Sure enough, I have a constant difference. I have the same difference showing up every time I subtract them. Let's do our first differences on this other table. So if I subtract these guys, 34 minus 26, yeah, that's an 8. If I subtract these guys, 42 minus 34 also gives me an 8, and 50 minus 42 also gives me an 8. Yay! So we found our first differences. In both tables, the first differences are 8, or 8 inches per chair if you want to make sure that you've got your units going correctly. So for each chair we add on, we have a difference of 8 inches. We're adding on 8 more inches. And so this is what we call first differences. If these numbers had not been the same, if I was like 8, 7, 6, what? Then this would not be a linear function. In order to be a linear function, you have to have a constant difference. Those first differences have to be the same every time. So here's the deal though, you gotta be careful with this. So Parks and Eva Cate agree that the table shown, so we have a lovely table here on page M2-14, they agree that the table shown represents a linear relationship because there is a constant difference between consecutive points, right? They keep getting 5, 5, 5 every time they subtract. That's great. So Parks, because we said this constant difference, this common difference is also our slope. So Parks claims that the slope is 5. And Eva Cate claims the slope is -5. Who's correct? And explain why. Hit pause, jot down your thoughts, hit play when you're ready to check your work. Well, guess what, guys? I noticed that as x was increasing, y was decreasing. My y values were going down, not up. So you know what that means? It means Eva Cate was correct. Yeah, the slope is -5 because as our x values were increasing, the y values were decreasing, guys. The 5 describes how steep the line is. And the negative describes the fact that it is decreasing in direction, that it's going down, not up. So you do want to watch out for that. Make sure you're catching that as x was going up, y was going down. So that means my slope is a -5. That means my common difference is a -5. Watch out for that. Watch out. So here's what I would like you to do. Number 6, and we'll wrap this bad boy up for the day. I would like you to do problem number 6 on page M2-14. I would like you to use first differences to determine whether each table represents a linear function, and then create your own table to represent a linear function on part D. So A, B, and C, use first differences, see if it works, if it's giving you a linear function, and then on part D, make your own table to make up your own linear function. So hit pause to work these out, and then hit play when you're ready to check your work. All right, let's find our common differences. So I'm going to find some common differences, and I'm going to use my pen to help me do that. So I'm going to subtract. So if I subtract, 30 minus 21 is 9. 21 minus 15, oh man, some days I just need a calculator. No, I don't. I can do it. 21 minus 15 is 6, and then 15 minus 12 is 3. Guys, my first differences are not constant. So I'm going to say, no, this is not a linear function. This is not a linear function. My first differences were 3, 6, and 9. That's no good. Part B. So again, I'm going to find the differences. It looks like 14 minus 18 is a -4. 10 minus 14 is a -4. 6 minus 10 is a -4. Oh, yeah. Yeah, I got the same thing every time. You know what that means? It means it's a linear function. Yes, this is a linear function. The first differences are -4. I was going down, not up, so my first differences were -4. Watch out for that. Part C, what do we got here? Well, let's find out. If I do 4 minus 1, I get 3. 9 minus 4 gives me 5. And 16 minus 9 gives me 7. You know what this means, don't you? It means it's not a linear function. Boo. So this table is not a linear function. My first differences were 3, 5, and 7. They were totally different numbers every time. So not a linear function. It's sad, but I mean, we can still love it and we can still be friends. It's cool. It's fine. And of course, the fun one was D, where you got to make up your own linear function. So I'm going to make up my own. I'm super lazy, so I'm just going to make my x values 1, 2, 3, and 4. Hey, that was really rough. For my y value, I want the difference to be the same every time. So I'm going to start with 25, because that's one of my favorite numbers. And I'm going to say that I want my common difference to be a +5. So I'm going to add 5. So 30, 35, 40. And that way, if I double check my common differences, I'm always going to get 5. And I'll be like, that bad boy is a linear function. Woo. You probably picked different numbers, and that's okay. The point is, I just want to make sure that my first differences were always going to be the same. That's how I know it's a linear function. Yay. All right, guys, as always, I hope you found this helpful. I hope you found this useful. If you have questions or concerns, please feel free to email me. And I'll see you soon. Bye. Okay, maybe bye. I will say bye. It will be bye. I just got to turn it off. Bye, guys.